Hello world, in today's video we continue talking about Newton's second law of motion. Please feel free to pause this video and try out the questions for yourself. So today's question goes something like, a block of mass 5 kilogram at rest on a rough horizontal table is connected to another block B of mass 10 kilogram by means of a light inextensible string which passes over a frictionless pulley. A force of 120 Newton is applied vertically upwards on block B as shown in the diagram below. And then it continues to say the kinetic frictional force between the surface and block A. Remember, for us to have kinetic frictional force, we must have a surface. So the kinetic frictional force is acting on this block because it's that one on a surface, just in case you missed that. So the kinetic frictional force between the surface and block A is 15 Newton, so we are given Fk. What is Fk by definition? Fk, or kinetic frictional force, is a force that opposes the motion of a moving object relative to the surface. Key, moving. So what this tells us is block A is moving. And because these two blocks are connected to each other, if A is moving, it means that B is also moving. So there was firstly one piece of information which says that the 5 kilogram is at rest. It means initially it was at rest. So it was initially at rest and is connected. So it was initially at rest and then it was connected to block B. Once it is connected to block B, it begins to have kinetic frictional force, meaning that once it is connected to B, it starts to move. So if you look at the diagram as a whole, a force F is being applied to the 10 kilogram block. As this force is being applied, it pulls block B upwards. Block B then pulls block A towards the left, and then block A then experiences kinetic frictional force. We cannot have kinetic frictional force if the object is not moving. And if you look at the diagram carefully, there's only one force which has the potential to get block A to move, which is the force which is along the string, the force which is known as the tensional force. So we are more than justified to assume the direction of motion of this particular system to be left for A and upwards for B. Very important. You cannot have kinetic friction if the object is not moving. If A was not moving, then they could have told us about the static frictional force, or perhaps the maximum static frictional force. So as part of the analysis, I'm going to start with the free body diagrams. But don't ignore the last part. It says that ignore the effects of F friction. It means when we draw these bodies, we don't have FA there. We are ignoring it. So I'm going to start with the free body diagram for A. So along the vertical direction, I'm only going to draw the vertical direction because we don't have a surface. So we have object, it's object B, sorry. I'm going to start with B. We have force applied. I'm going to copy it from the diagram. The force which is always there and always vertically downwards, that is the weight. And because there's a string, it means that we have tension. How do we draw the tensional force? Remember that the tensional force is along the string away from the object. So I'm going to draw it in green. So that is tension. And then now for block A, it's on a surface, so parallel to the surface, x-axis. Perpendicular to the surface, you have y-axis. Where they meet, you put the object. Start with the force which is always there and always vertically downwards, which is the weight. And what else do we have? We have the normal pointing away from the surface perpendicular to it. What else do we have? We have the tension along the string away from the object. That is the tension. I have assumed the direction of motion of A to be left, so it means that kinetic friction will be opposite to the direction of motion. Okay. I think we have done a lot there. Maybe we can try to find or include the magnitude of these forces on the diagram. So for the weight for block B, that is mg. Let me write it in red. That is mg. What is the mass? It's 10g. It's a constant. Therefore, the weight will be 98 newtons. Do we know this force? Yes, it's given as 120. Oh, I did not write normal there. That's normal. On the next free body diagram, do we know the weight? Yes, it's mg. If you calculate it, you'll get 49 newton. Kinetic friction, it's given as 15 newton. Do we know the normal? We can calculate the normal. How do we calculate it? Remember, F net is equals to, is the block moving along the y direction? The answer is no. So sum of forces along the y direction will be 0. We have normal minus the weight equals to 0. That is n minus 49 equals to 0. Therefore, the normal will be 49 newtons. So I can include this. This will be 49 newton. I think we have done a pretty thorough analysis. The first one says define normal force. I know you've got that one in the pocket. The second one says draw a labeled free body diagram showing all forces acting on block B. And it says 3 marks, and they didn't say anything about relative magnitude, so we can apply 1 force, 1 mark. If we look at the free body diagram, indeed we have 3 forces, 1 mark for each. And it says calculate the magnitude of the tension force acting on block B. Remember we said that the tension is the same throughout the string. And the tension that we are talking about, which is acting on B, there's the tension there. That is the same tension that is acting on A. Remember, I also said if you see 2 bodies in the diagram, it just means that you're going to need to solve simultaneous. You're going to need 2 equations to solve the problem. So it means we can define Newton's first or Newton's second law of motion for each of these objects. If we look at the statement, it says that 5 kilogram was initially at rest. From the last statement, we are getting a sense that the object is now moving. So from a velocity of 0 to a velocity of non-zero, that is an increase in velocity. So clearly, this object is accelerating. Both objects A and object B, they are accelerating. Then we rule out Newton's first law, we apply Newton's second law. Never assume that the system is moving with constant velocity or the system remains at rest. Over here, we started with rest. It is now moving. So clearly, the system is accelerating. If you are unsure, you can always start with Newton's second law. So you're going to have, for that question, F net. Let me clear here. I'm going to start with block B. F net along, for B, I only have one direction. F net along the y is equals to mass multiplied by acceleration. Along the y, I have F. I'm going to take upward as positive. That is the assumed direction of motion. Plus minus tension plus minus the weight equals to mass multiplied by acceleration. Now I can sub in. I have 120 minus, I don't know the tension, minus the weight. I found it to be 98 equals to 10 multiplied by the acceleration. Now I can simplify this nicely. I'm going to have, let me grab a calculator. 120 minus 98, I get 22. So I have 22 minus t equals 210a. I'm going to leave it at that. I'm going to call that equation number 1. I've got equation number 1 by defining Newton's second law for block B. Now we're going to move to block A. Block A. Is block A moving along the y direction? No, not even possible. Can only move along the x direction. So we're going to sum forces along the direction of motion, which is x. That will be equals to mass multiplied by acceleration. I assumed the direction of motion to be left, so I'm taking left as positive. Towards the left, I have the tension. Tension plus minus Fk equals to the mass for that block. I think it's 5. You have 5 multiplied by acceleration. So we can sub in there. We have tension. Positive times negative is negative. Fk was given as 15. That it will be equals to 5a. If I make tension subject of the formula, it means tension is equals to 5a plus 15. That is my equation number 2. So what I'm going to do is I'm going to take this tension. We are saying tension is equals to this much. So where I see tension, I'm going to replace it with 5a plus 15 in the first equation. So I'm going to say sub equation 2 into 1. Remember, we spoke about this the other day. We have 22 minus t equals to 10a. We said when you sub in, please put the brackets. So I'm going to put the brackets. I'm going to have 5a plus 15 equals to 10a. Now I can group like terms. I have 22 minus 5a minus 15 equals to 10a. 22 minus 15, let us see. 22 minus 15, that is 7. I have 7 equals to 10a plus 5a. So that is 7 equals to 15a. If I divide both sides by 15, 7 divided by 15, I get that the acceleration will be equals to 0.46666. I want to keep as decimal places as possible. 7 meters per square second. So because my acceleration is positive, it means the assumed direction of motion was correct. Okay, it's fine. Now we can continue. There's the acceleration, but the question actually asked for the tension in B. So I can back substitute that into equation. I'm going to say sub A into equation 2. So this means that the tension is equals to 5 multiplied by 0.46667 plus 15, which will be equals to, let me see, that is multiplied by 5 plus 15. If I round it off to 2 decimal places, that will be the magnitude of the tension. Okay, let's just verify if everything is good. We have 120 minus 98 minus tension. 120 minus 98, it is indeed 22. And then over here we have kinetic frictional force of 15. Everything seems perfect. Then we have 22 minus 15, that is 7. Okay, everything looks good. So this will be the magnitude of the tension. So indeed, the system is accelerating and the assumed direction of motion was positive. But since we are given kinetic friction, we can play around with this question. We can try to calculate the coefficient of kinetic friction. Feel free to pause once more and calculate the coefficient for yourself. If we want to calculate the coefficient, please note this question is not being asked. I'm just adding the question. The only equation which has mu k, I don't know how it is going to appear on your data sheet. I'm going to write it as fk divided by the normal. Do we know fk? Yes, it was given as 15. Do we know the normal? Yes, we calculated it. We found it to be 49. Therefore, mu k will be equals to, remember it should be greater than 0 but less than 1. 15 divided by 49, I got 0,3. 1. And remember that mu k is unit less. So let us say, because we know that the object was initially at rest, initial velocity is 0. So I'm going to say, determine the velocity of block A after traveling 5 meters. Calculate the velocity of block A at point X after traveling 5 meters. Okay, so if I want the velocity of block A, this is a velocity at a later stage. So I'm going to call this final velocity. So I'm asking us to calculate the final velocity. And what do we have so far? Let us write down the data. I'm going to solve the problem somewhere down here. Do I need the free body diagrams? Yeah, I think I'm going to need them. Okay. So final velocity is what I'm looking for, but what do we know? We know the initial velocity. What else do we know at this point? You and I have just calculated the acceleration. We said acceleration was 0,4666667 meters per square second to the left for block A. What else do we know? I have given you the displacement, the shortest path between 2 points. That will be 5 meters. Remember, direction of the displacement is the direction of motion. So this will be left. I'm going to take left as positive. Which equation of motion has 1, 2, 3, 4 variables? That is V final squared is equals to V initial squared plus 2 acceleration multiplied by displacement. This is what we are looking for. This is equals to 0 squared plus 2 multiplied by 0,4666667 multiplied by 5. And then you can take a square root on both sides. Therefore, final velocity will be equals to. Remember that if you look at this from a mathematical perspective, if you take a square root, we are going to get two possible answers. It's either we are going to get a positive answer or a negative answer. Whether we choose a positive or a negative, it will depend on the direction that we have picked. So we said that left was positive and left is the direction of motion. So the expectation is the final answer should be positive. So let me just quickly grab my calculator. Calculator, where are you? Okay, my calculator seems nowhere to be found, but I guess that's not a problem. I'm just trying to avoid using the one on my device. Okay, so I found my calculator. Square root of 0 squared plus 2 multiplied by 0,46667 multiplied by 5. I found that my answer will be 2,16 meters per second left. That will be the velocity at point X. And I can actually add a lot of questions here. My next question could be, how long did it take for block A to reach point X? So now I'm looking for delta T. What do I know? I know the initial velocity. I know the displacement. I also know, what else do I know? I know the acceleration. So there are two equations that you can go for here if you want delta T. Number one, you can either use V final equals to V initial plus acceleration delta T, or you can use delta X equals to V initial delta T plus half acceleration delta T squared, whichever one that you're comfortable with. I'm going to go with the second one. So if we use the second equation, then we have displacement equals to initial velocity time taken plus 1 over 2 acceleration time taken squared. This is positive 5 equals to, this whole thing will be 0 because initial velocity is 0, plus 1 over 2 acceleration. We have it from the solution multiplied by delta T squared. So what we can do is multiply both sides by 2. You're going to have 10 equals to, remember when you do this calculation that time can never be negative, delta T squared. So for this part, we're going to take the positive solution. So what I'm going to do is I'm going to divide both sides by 0,46667. And then after doing that, I'm going to take a square root on both sides. Therefore, delta T will be equals to square root of 10 divided by 0,46667. That is something approximately 4,63 seconds. Okay, and I could add one more question. I can ask you to draw the velocity time graph for block A. So velocity time graph would look something like this. This is velocity in meters per second as a function of time is in seconds. We know initially this object was at rest and the velocity increased. So as explained in the previous video, that the velocity time graph will be a straight line graph and the gradient represents the acceleration. So to reach point X, I can include the times there. We have 4,63, and at that point, we have said that the velocity was going to be, I don't remember the value, but it was 2, something. And then that will be the graph. And we can play around with this question as much as possible. Let us say the string breaks, for example. Let us consider that case. Assume the string breaks. Okay, I have hidden this question here because we haven't spoken about Newton's third law. I'm going to come back to it someday. So assume the string breaks. Question might be, what will happen to the kinetic frictional force acting on block A? If the string breaks, what it just means is, I have removed a huge chunk. If the string breaks, it means that the tension will be 0. And then this is the free body diagram that we are going to be having. Remember that Fk is only affected by two things. Fk is affected by mu k affected by the normal. If the string breaks, it's still the same block, made of the same material, still on the same surface, made of the same material. Mu k will remain constant. And if we look at the normal force from the diagram, it will still remain the same. So if the string breaks, Fk will remain constant. Okay. Perhaps the question might also be, what will happen to the velocity of the block? Okay, let us consider that case. If the string breaks, what will be the net force? If we look at the diagram from definition of net force, the net force will be equals to Fk. That is the only force now along the direction of motion. Remember where the block was moving. When the string broke, the object was moving to the left. This is the direction of motion. Now the string breaks, the object continues to move forward. There's a property of an object to resist a change in a state of its motion, which is known as inertia. So this object will continue moving forward due to its inertia. That will be the direction of motion. But what will be the direction of the net force? Because net force is now equals to Fk, it means the direction of the net force will be towards the right. What do we notice? We notice that the direction of velocity, the direction of motion, and the direction of net force, they are opposite each other. Every time when these two things they're in opposite direction, it means that the object will slow down, and the opposite is true. If they are in the same direction, the object will speed up. Okay, so if the string breaks, the object, point number one, the object will continue moving left due to its inertia, due to its ability to resist the change in its state of motion. Point number two, what we have seen is block A will move with decreasing velocity to the left, and then after a long time, what is going to happen? The velocity will decrease until block A comes to rest, and we can draw the velocity time graph for block A the instant the string breaks. From the instant the string breaks, the velocity time graph might look something like this. Velocity in meters per second as a function of time in second. Finally, the block comes to rest. Okay, that's it from me for today. In the next video, we're going to look at Newton's third law of motion. Thank you and bye.